This will be an important video in which I'm going to explain how to go about doing calculations for equilibrium problems, right? These are some of the most complicated problems that we run into over the length of the course, and like a lot of courses, we save those for the end. In this case, that's because they really rely on knowing a lot of things about stoichiometry and some of the stuff we learned in the beginning as well. Last time I discussed what would happen if the equilibrium constant was enormously big or very, very small, right? And that in that case, we would pretty much have only products if it was really large, only reactants if the equilibrium constant was really small. If the equilibrium constant is not either of those extremes, if it's, gosh, I guess the perfect middle of the road example would be if it's 1, then we would expect to have a mixture of both things at equilibrium, okay? The equilibrium constant tells us the relationship among the final concentrations, right? Because it's the ratio of the product concentrations over the reactant concentrations. Those concentrations are often raised to different powers, which means it's not quite as easy as just saying like, this is just take the concentrations and divide them. The way to go about these problems is two things. If you're solving an equilibrium problem, meaning if there's an equilibrium two-way arrow in a reaction, and you're trying to find out either the value of the equilibrium constant or the concentration of one or more of the substances when it gets to equilibrium, there's two things I'm going to encourage you to do every single time. Number one is somewhere along the way, you're going to have to write down the expression for the equilibrium constant. So I like to do that right in the beginning and just remind myself that's one of the things that I know. The other is then we're going to use stoichiometry ideas to relate the changes in the different concentrations, right? There's usually two ways these problems go. Either there's a way we can find all the equilibrium concentrations, and in that case, then we can solve for the equilibrium constant, or if we know the equilibrium constant and we know the original amounts of stuff, then we can, in most cases, solve for the equilibrium concentrations, okay? The second version is a little bit harder than the first. What I'm going to encourage you to do in every one of these equilibrium problems, besides writing down that equilibrium constant expression, is to set up what in chemistry teaching circles are usually referred to as ICE tables. The ICE is an acronym there. It stands for initial, change, and equilibrium. So we're going to set up a table that has basically 3 rows in it. The concentrations when the reaction starts, what's going to happen to them, that one we're going to figure out from stoichiometry, and then what are they going to be at equilibrium, okay? The best way to illustrate that is examples. And so the bulk of this video is just going to be 2 worked out example problems, one in which we find the equilibrium constant and the other in which we know the equilibrium constant and solve for the concentrations. So let's just go ahead and do that. First up says we have an equilibrium here, right? It's got SO3, sulfur trioxide, an equilibrium with SO2 and oxygen, all right? It says if we put 3 moles of SO3 in an 8-liter flask at fairly high temperature, 1150 Kelvin, we let that equilibrate. So we let it react until the concentrations are no longer changing. And this says we have some way of measuring the amount of oxygen that's in the flask at the end, and it says it's 0.58 moles, okay? And our task is to find the value of the equilibrium constant, KEQ, for that reaction, okay? So there's 2 things we can say we know, and I'll flip to another slide so I have more room in a second, but I can start off by saying I know that the expression for that equilibrium constant is the product concentrations over the reactant concentrations, and everything raised to powers where the powers come from the stoichiometric coefficients, right? So that's pretty literally the only equation I can write down for that equilibrium constant. So in order to solve for the equilibrium constant, I'm going to have to be able to find all of those 3 concentrations at equilibrium, all right? The square brackets in there, just like in kinetics, they still mean concentration. They mean molarities, okay? So one thing I'm going to need when I set up my chart on the next page is I'm going to need to know that the 3 moles of SO3 is in an 8-liter flask, and that means that the initial concentration of SO3 is going to be 3/8, right? So I could call that something like the concentration of SO3, and I'll put an I on there for initial, all right? One other thing that we know right now is we know how many moles of oxygen we have at the end, right? So if I take those 0.58 moles of oxygen and I divide those by the 8 liters, That says that I have a number for that over here someplace, 0.0725. All right, and that thing is equal to, let's call it the O2 concentration when it gets to equilibrium, okay? So those are the things I know. All right, those two numbers, the 0.0375, the 0.375 rather, and 0.0725, those are going to pop into my work on the next slide. Okay, so just be aware of where those are coming from. I'll try to give us a reminder when we get there. So here goes. I know down here I'm going to rewrite my equilibrium constant, which says that's still equal to the SO2 squared, the O2 over the SO3 squared. And again, that's only going to be true when they get to equilibrium. So what I'm going to do is I'm going to use the equation that's on the screen up there as sort of the headings, and I'm going to write out my, my table here. Okay, so I'm going to do an I, which again, that stands for initial. Right? At the beginning of this reaction, what do I have? We just figured out I have 0.375 molar, because the things I'm putting in here are concentrations, right? That's the original concentration of SO3. At the beginning of the reaction, there is no SO2 or oxygen because we didn't put any of those in the container, right? All that's in there is what we put in. So those are 0. Now, I do my change row. Right? The change row is one we're going to do just basically by thinking about how stoichiometry works, okay? Right now, I have material on the left-hand side of the equation. I have SO3. I don't have any SO2 and oxygen. So if any reaction is going to happen, it's going to have to make SO2 and oxygen. Those two are going to have to go up, and that means the SO3 concentration is going to have to go down, right? Because I can't make the SO2 and the oxygen without taking away some of the SO3s. So I know this one is decreasing, and I know these two are increasing, okay? Next up, I know from those molar coefficients, the 2 and the 2 and the 1, that says that the ratio of those changes, the SO3 and the SO2 are going to change by twice as much as the oxygen does. I want to put all the changes in there, and I want to put them in terms of one variable. That's going to be the thing we don't know that we're going to end up solving for, okay? So what I like to do is I like to use the coefficients and just make them the coefficients on a variable, which pretty much always we call x. And so if the oxygen goes up by an amount of x moles per liter, well, every time I make one oxygen, I make 2 SO2s. So this has to go up by 2x. Right? Every time I make 2 SO2s or 1 oxygen, it costs me 2 SO3s. So this has to go down by 2x, okay? So those coefficients here are really just the coefficients that are balancing the equation up above, all right? If I put minus x for the SO3, that won't make the problem come out wrong. It'll just make it a little bit more awkward because I'll have a fraction on the O2. Right? If I put minus x on the SO3, then I'd have to put plus 1/2 x on the oxygen. Like a lot of people that have experience doing these problems, I don't like to put fractions in there because they just make me more likely to mess up the arithmetic later. So I always do them this way, but it isn't wrong if you do it with a fraction in there. Then I'm going to put what happens when it gets to equilibrium. This just says we know what we had in the beginning and we know what happened to it, right? So all I have to do now is sum the columns to get what I have at equilibrium. So this is 0.375 minus 2x. This is 2x, and this is x, all right? So now, in order to get to be able to solve for the equilibrium constant down on the bottom, I have to know a value of x, right? Because I need numbers to put in there for the equilibrium constant. If I put those things in there with x's in them, I can't solve it for a numerical value. This is where we have to remember what else we know. So let me flip back to my first set of stuff here, right? Here, I said, from the fact that we knew the moles of oxygen at the end, I know that the equilibrium concentration of oxygen is 0.0725 molar, okay? Now, I also know that that's equal to x. 0.0725 is the number, yes. 25, really, I'm writing numbers. So that tells me what x is, right? So if this is now equal to x, because it's that concentration, we said it's equal to x, we also said it's equal to 0.0725, so those two things are equal, okay? That makes these concentrations 0.145, and over here, I get, I'm struggling to find a number, I get 0.23. right? Those are all molarities. One thing you'll be very happy to learn is that equilibrium constants, we always write equilibrium constants without any units, okay? I don't want to get into the details of why that is, but we don't have to carry the molarity units through this or anything like that. So now all I have to do is put in my numbers down here. I have to be careful doing the arithmetic because I've got exponents and all that, right? So this one is 0.145. And that's squared. This one is 0.0725. And we could, if we wanted to, we could have just, left this in terms of x and put in the value for x. I tend to do them this way by turning them into numbers. I like to make sure that all the concentration numbers are positive, for example, because they have to be, right? 0.23 squared. And if I multiply that out according to my notes over here, I get a value which says it's equal to 0.02. I have 0.288 in my notes. Okay. You can't really, there's not a good way to get a handle on just what sort of magnitude can equilibrium constant be, right? In the previous video, I showed you examples that went from 10 to the minus 30 something to 10 to the plus 140 or something like that, right? And so there's a huge range over which they could vary. In this case, if I just look at the concentrations, it looks like the concentration that stayed on the left-hand side is bigger than the concentration that went to the right-hand side, right? So that suggests that the equilibrium constant should not be really big because I still have more stuff on the reactant side, right? And the equilibrium constant is products over reactants, so more on the reactant side should make it tend to be smaller. And so it seems like it's reasonable. That process of setting up that table and just using it to organize what do I know and what do I need to know, that's the best route for getting through an equilibrium problem without just making a mess of things, okay? If you haven't done the problem before or you're not used to these, you can pretty easily get yourself to the point where you have all these entries in the table. Then you just have to say to yourself, in this direction, if we're trying to solve for the equilibrium constant, there's got to be a way to figure out one of those final concentrations, because as soon as I know one of them, I can use that to know what X is, right? And then I can solve for the other concentrations. So that's the best plan for solving in that direction. The second option on these problems is one that's usually a little bit harder, and that is to solve for the equilibrium concentrations, okay? So here I have a reaction, carbon monoxide and water reacting to make CO2 and hydrogen. This reaction actually has a name. It's called the water gas shift reaction. And it says we're going to put 1 mole each of CO and water in a 50-liter container at 1,000 degrees C. We know the value of the equilibrium constant this time, and we're going to try to solve for all of the concentrations of the 4 substances, right? So again, I'll just turn these into molarities. If I put 1 mole, or just, I've got a 1, I guess, 1 mole in 50 liters, that's pretty easy. That's going to be 0.02 molar. Right, so that's equal to the initial concentration of both the CO and the water, because it just says we happen to have put in equal amounts of those, right? There's no rule that those two things had to be the same. If they weren't the same, it would make this problem a lot harder to solve, is what I'll say about that. And so there's a reason why I picked it to be that way. The equilibrium constant is 0.58, right? We'll write the expression for that in a second, but that's just going to be the CO2 times the hydrogen concentration over the CO and the water concentrations. You'll notice that, like in kinetics problems, the temperature is often stated in an equilibrium problem. We're not multiplying by the temperature, dividing by the temperature, but the value of the equilibrium constant would change if we change the temperature, okay? Basically, that's because rate constant change when you change the temperature, right? And we showed in the last video that one way to think about that equilibrium constant is as the ratio of the forward and backward rate constants, okay? So those can change and not necessarily by the same relative amounts, right? Usually not by the same relative amount. So the equilibrium constant will almost always change its value if we change the temperature. We'll talk a tiny bit about that at the very last moment of the semester. All right, so here is my reaction. I am now going to put down here my equilibrium constant expression because I'm going to need it sooner or later, right? This is CO2, hydrogen. This is a relatively friendly one because I don't have, I have only first power concentrations, right? Because I don't have any non-1 coefficients in my equation. And all that stuff is equal to 0.58, right? Because that was the numerical value that was given in the problem, okay? So now we're again gonna set up our table. We're gonna do our initial stuff, our changes, and our equilibrium, okay? Initially, we said we put in, and we just figured out these are 0.02 molar and 0.02 molar for both of the things on the reactant side, right? We did not put anything on the right-hand side, so those are going to be 0. Here, my changes are relatively simple, right? Because all my coefficients in my equation happen to be 1. So that's nice and friendly. So I know that the ones on the right have to go up because they're 0. You can't take stuff away when it's not there, right? So there's no way the concentrations of the CO2 or the hydrogen could possibly decrease. So I have to take away CO and water to make CO2 and hydrogen. So these are going to be minus X, plus X, and plus X. All right, that makes my equilibrium. And again, this is just taking the sum down each column because what we have at the end is what we had in the beginning minus the part that went away or plus whatever we added, right? And so that says I get these things. Right now, I don't know any of those concentrations, right? I know nothing about those final concentrations. So I can't just pull a number for X out of someplace. I don't have to because I now know the equilibrium constant, right? So now, borrowing from below there, I'm going to say my equilibrium constant, which is equal to 0.58, is equal to, what's it equal to? It's equal to X for the CO2 concentration times X for the hydrogen concentration over 0.02 minus X, and I have that same term twice as well, okay? In this case, I have those terms duplicated because the stoichiometry is all 1-to-1 and because the initial concentrations of the two things on the left-hand side were equal, right? That actually makes the problem much simpler. At this point, if I look at that equation, that's an equation, an algebraic equation with just one unknown, right? X is the only thing in there that's not just a number. So we can solve that for X. We can say that's equal to X squared over 0.02 minus X. Also squared. There's two ways to solve this, the easy way and the hard way. I'm going to vote for the easy way. There isn't always an easy way available, but there is in this case. The expression on the right-hand side there is a perfect square. And again, that's a result of having made those two initial concentrations be the same together with the friendly stoichiometry. Because that's a perfect square, the simplest route out of here is to take the square root of both sides, right? So if I take the square root of this, that'll give me that'll be equal to the square root of 0.58. Okay, and when I do that, I get, what do I get? I get X over 0.02 minus X is equal to the square root of 0.58, which is still just a number. And if I solve that according to my notes, that gets me to X being equal to, what do I get for X? I get 0.0086. All right, so up here, I wanted the final concentrations, right? So that gives me that these two are both going to be 0.0086. And the two on the other side, these two, when I put the numbers in there, those are going to be 0.0086 0.0114. And those are all molarities because that's the unit that we're working in on those, okay? It's important when you're doing a problem like this, a couple of cautions. One is when you get to the final answer, sometimes you solve for x, and in some cases, solving for that x variable can be a lot more work than it was here. It's not necessarily going to be the answer to the question, right? So if this question, if it was like in OWL or in a quiz or what have you, and it said, what's the final concentration of CO, then that's a different number, right? It's not hard to get from x to 0.02 minus x, but you do have to do that step, right? So do make sure that you're actually getting to the final answer. Second thing, if you don't realize that you can take the square root of that, there's nothing wrong with that. You can do the quadratic formula. If you're like me, your chances of getting it wrong that way are greater just because there's more things to type in the calculator and what have you, right? If you do solve the quadratic formula and if you end up with two roots, the way to distinguish between them is to say that the value of x, if we set it up like I am, I've set it up so that x has to be a positive number, right? Because x is the amount of stuff that actually went to the right-hand side, and that can't be negative, okay? And so it has to be a positive number. X also can't be bigger than 0.02 in this problem, right? Because all the concentrations have to end up being positive. It is generally the case if you do get two roots that one of them will give you at least one negative concentration, and that'll mean it's an invalid result to the problem because that's a non-physical event, right? You can't have a negative concentration of anything. All right. I confess this last one is a relatively simple version of the problem. We will, moving forward, take up some that are a little bit less algebraically friendly than this. But the fundamental structure of how we did these two problems is what I would really like to urge you to do for every single equilibrium problem, right? Even if you're doing one and you think it feels easy and you're thinking I can do it without making that table, I really encourage you to just say, no, that's how I'm going to do it, because it's the best way to organize all the things you know and figure out, okay, what do I have to actually find to be able to solve the problem.